Welcome to our wrap-up of Week 5. This week we examine the basics of correlation and simple regression. So by now you should have a basic understanding of how correlation is used to observe non-manipulated variables as they take place in real time. To review, in research we use correlation to describe the relationship between two or more variables that appear to occur or react to each other in a consistent fashion, resulting in one of two explanations. First, the variables are related and can be measured and or described. Second, the variables and or relationship are random events. Correlation is commonly utilized for establishing relationships regarding theory, prediction, reliability, and validation measures. Once established, these outcomes are often followed up with more stringent experimental research designs, such as randomized controlled trials, in an attempt to establish true causality. Remember that correlation itself does not infer causality. I've included a brief YouTube clip below. Check it out. It's kind of a humorous way to remember this statement. We also took a look at regression analysis. Linear regression attempts to model the relationship between two variables by fitting a linear equation to observed data. Scatter plots are helpful tools that can show us the direction, strength, form, and outliers we may have within these data sets. Linear regression models can then be used to make predictions. If we know the value of x in an established regression equation, we'll be able to predict what the value of y will be. We had a few questions regarding regression lines. A regression line is one that best fits the data and has the smallest overall distance from the line to each one of the data points. It reflects our best guess as to what score on the y variable would be predicted by a score on the x variable. These lines are commonly constructed using the least squares method. During your on-site session, Dr. Capper will be showing you how to construct these lines using SPSS. For your resource, I have included a brief tutorial on how the least squares method is calculated so you can have an understanding as to how the output data used can be used to construct the line that is obtained. Lastly, I'd like to revisit the standard error of the estimate in a linear regression. In this slide, we have some example data that attempts to correlate vertical jump height to performance on a triple hop distance. From the data points, we can visually see that the data appears to move upward in a linear fashion. Standard error of the estimate is a measure that tells us about the fit of the line to the data. When visually examining a scatter plot, each point is an actual y value. If you move in a straight line, up or down, from a particular scatter plot point toward the regression line, the point at which you come in contact with the regression line is your predicted y value. The distance between the actual y and the predicted y is your error. So if I put a few arrows in here, we'll just pick some random points. These I put on the screen here to just kind of illustrate to you. That is the amount of space between the actual calculated y value of the regression line and the actual data point itself, the plot, and that is considered the error. That's the error that we're talking about here. So the standard error of the estimate is basically the standard deviation of this error. It tells us about the dispersion of all the actual y's as a whole from the regression line. The greater the dispersion of the data points from the regression line, the higher the standard error of the estimate.